So we have been done, I think, with 5 properties of determinants. Let's just first of all revise all of these properties. We had, so first property was oh yeah, Faisal, we have just started. So yes, properties of determinant. So first property was, if you take transpose over any determinant, then if you take a matrix and take its transpose, both will have same value. Right? If we find out the determinant for both of them. And second was, if any 2 rows or any 2 columns are interchanged within a determinant, then the sign of determinant changes. So let's say you have solved one determinant and the value of the determinant is 8. Now, if you interchange any 2 rows or any 2 columns, the value will be -8. Right? Then the third one was, if any 2 rows of columns of a determinant are identical, then the value of that determinant becomes 0. Right? So if there are any 2 rows or any 2 columns and they are exactly the same, or in fact, they are proportional to each other. Like if one column is, or let's say one row is 1, 2, 3, 1, 2, and 3, and second row is in multiple of 1, 2, 3. So let's say k times 1, 2, 3. And it can be anything. It's a multiply this by 4. So 4, 8, and 12. So if the second row is a multiple of the first row, or let's say any 2 rows are same or they are multiple of each other, in that case, the value of that determinant will be 0. Right? And then the fourth one was, not just a minute. Okay, I think one more student is joining the class, but it's not able to join it. So yeah, so fourth one was, if each element of a row or column of a determinant is multiplied by a constant, then the value of the determinant gets multiplied by k. So we have established the fact that we can take common from either any row or any column, and if there is a determinant whose value we know that the value of this determinant is delta, and let's say there is another determinant in which one row or one column is a multiple of this, right? So we can take that k common and the value will be k delta, right? And we have shown that we have, I have shown you that how can we use this exactly. So one way is this, that if a row or column is multiplied by some number k, then the whole determinant gets multiplied by that number k. And the second use was that we can take common, or we can, if we are multiplying k, then we can multiply either in a row or in a column, and in any column or any row which we want. And third one was, we can take we can take common from either any row or any column, right? Now, and we have also solved some of the questions based on these properties, and we have written this. Is different, and the rest of the part of that determinant is same, right? So we can, guys, am I audible?
Yes, sir.
Okay. So we can only add or subtract two determinants when one row or one column is different and other rest of the part of that determinant are same. Right. So now coming to the sixth property, which is the last property of this, in this properties of determinant. And the property says that let's say you have a, first of all, let's understand the use of this property. So let's say we have some determinant, 1, 2, 3, 4. Now, we haven't talked about this in metrics. You guys should have known about it in metrics, but as your students reduced, so that is why we have talked about this. This is called elementary row transformation or elementary column transformations. So, what are elementary transformations? First of all, we can change any row or any column of a matrix by taking the another multiple of another column or another row. For example, this is a let's take any 3 by 3 matrix, or rather 3 by 3 determinant row. I'll tell you first of all directly. I mean, first of all, we will understand what is an elementary transformation. Then we will understand what is the property that it in what property holds in determinant in that case. So elementary transformation is something in which you change one row with the help of another row, or one column with the help of another column. For example, we have 3 rows and 3 columns here. Now I want to change R1 with this R1 plus or minus, however I want, K times with the help of some other row, maybe row 2, maybe row 3. Now let's see, I want to change it like this. Why we are changing it and why we are doing this, we'll talk about later on. But this is called elementary row transformation. Now I have transformed row 1 with the help of row 2, or rather with the help of any multiple of row 2. Right? Similarly, I can also change any column. So let's say I am changing column C3. C3 changes to C3 plus twice over C. I can do this. If I'm doing this, if I'm performing this operation on any matrix or any determinant, I'm basically doing elementary transformation. If I'm doing this with a row, then it is called row transformation or elementary row transformation. And if I'm doing it on a column, if we are performing this operation on a column, then we will call it as for elementary column transformation. Right? Now, the use of this in determinant is if you change any row or if you change any column with elementary transformation, the value of that determinant will never change. Value of the determinant will never change. Now, why is it happening? We will talk it about. But first of all, we can apply any elementary transformation in a determinant. It may be row, it may be column, but the value of that determinant will never change if you apply any elementary transformation on that matrix or rather determinant. Now, why is it happening? Let's talk it about. First of all, we have considered this. Right, this is properly actually. Can you guys please find out the value of this determinant? This determinant 156378492. Please find out the value. Everyone, please solve this and tell me the value. You can either text me or just directly tell me.
This method.
Sorry, Showers, you're not audible. You have to find the value of this determinant. You can use any method if you are asking which method you need to use. What's the value? I think it's 2 if someone is solving. It's
Yes,
coming
sir.
out as 2. Yeah. So now let's apply this to what we have talked about. How now I am applying a elementary row transformation on this determinant, and I will show you that the value of this determinant doesn't change. Let's apply this row transformation. Now, how are we going to apply this? First of all, whichever row you are changing, just leave that row and write another rows as it is. So we are not changing second row and third row. We are using second row to change row 1, but we are not changing row 2, right? So row 2 and row 3 will be as it is. They are 3, 7, 8 and 4, 9, 10. Now we are changing row 1 with the rule this. Right. So row 1, that is you have to take the element from row 1 minus twice of row 2. So this should be 1 minus twice of row 2 should be 2 into 3, which is 6. So the value here should be minus 5. In this way, you have to change every element of row 1. So second will be 5 minus 14. 5 minus 14, which would be minus 9. Third would be 6 minus 2 into 8. Row 1, take an element from row 1 and take the corresponding element from row 2 and multiply it by minus 2 and then add them. So 6 plus minus 16, or rather 6 minus 16, which would be minus 10. Right? Now I have performed this operation on this determinant, but if you check it, the value still should be 2. Let's solve it. So this should be minus 5 into 70 minus 72. Then this should be plus 9. There are no zeros, so I'm directly expanding it along the row 1. So this should be minus 5 into 70 minus 72 plus 9. There should be a minus sign before minus 9. So it should be plus 9. And this should be 30 minus 32. And this should be minus 10 and 27 minus 20. So it should be what? Minus 2 plus 10 minus 18. And this should be plus 10. The value is still 2. Right? So if you perform, you can also check for this operation, the value still remains same. So if you perform any elementary transformation on a determinant, the value doesn't change. So the rule is simple, right? Now, how are we doing this rule? And we will talk about these things, but how to use the rule, now you know that, right? Now, why is it happening? Very simple explaining. It is related to our previous properties only. You can use this as an example actually. Now I'm writing out the rule. So the property says if there is a determinant which is A1, A2, A3, B1, B2, B3, and C1, C2, C3, right? And there is some delta, or rather call it as delta dash, right? Which is transformed as A1, or rather I can, sorry. If we perform any any elementary row transformation So let's say we have written a delta dash, which is sum this. So can you tell me how did I obtain delta dash from delta? Which operation did we apply? How can I get delta dash from delta? Delta is A1, A2, A3, B1, B2, B3, C1, C2, C3, and delta dash is A1 plus K times C1.
R
R1, yes. So we have changed rows with the rule
is equal to R1 minus 2R.
R1 plus K times R3. No?
Yes, yes.
So we have changed R1 from R1 plus K times R3, right? And that is how we have obtained this delta dash. So we are saying that delta and delta dash are. This is a basic result, right? So we can use these 6 properties to actually, first of all, find out the values for some determinant. So now let's understand one thing before we proceed. Uh, we have been, sometimes we have to solve the determinant, and sometimes it will be written that find out the value, or rather prove that this determinant is equal to this without expanding. So whenever the word without expanding will be used, it means that you can't solve your determinant using those cofactors and minus whatever. We have understood the rule before, how to expand a determinant, but you sometimes it will be written that you don't need to expand the determinant and show this expression is equal to some value. So in those cases, we have to use the properties of determinant. How will we use? We will learn through some examples. So let's first start with some questions, basic questions. Uh, start with example 11 only. So it is given on your NCRT page number 115. If you guys have NCRT, please open it. Page 115, example 11. So it is, we have to prove actually.
So can you scroll up?
Yes, you are writing.
Yes.
No.
Yes, I finished.
So let's start with some of the examples, and it will be either written, prove that, either the language will be this, or show without expanding. Both means the same. And you have been given a determinant. Yes. So a determinant is given whose first column is A, 2A, 3A. Second column is A plus B, 3A plus 2B, and 6A plus 3B. And third column is A plus B plus C, 4A plus 3B plus 2C, 10A plus 6B plus 3C. And we have to show that the value of this determinant is A cube. Now, one way is we can find out the cofactors, and using that we can expand this like this: 3A plus 2B into 10A plus 6B plus 3C minus 6A plus 3B into 4A plus 3B plus 2C. And then we'll go with minus times A plus B and this. Now you can understand, this is visual, certainly visual, that the value of this determinant, we can solve this value, but this will be hard to find, right? It will take like around 2-3 minutes, easily 2-3 minutes to solve the whole expression, and then we may be wrong in between. So this is not a nice way, or this is not a wise way to calculate this value. Right? So first of all, why do we need these properties of determinants? The explanation is very simple, that we can easily use these properties of determinant to solve rather complex determinants. Maybe the determinants look like a very big determinant, but the values may be simple, right? So we can use, or we can simplify our determinant, in fact, any determinant, using these properties of determinant to solve them easily. And also, you can't solve it like that. This is particularly in these cases when you are asked to show without expanding. You cannot show it using the help of extension, right? And a 4-mark question will be there from this chapter. Particularly, I'm talking about CBSE boards right now. So a 4 marks question will be certainly from there, and you can't use these extensions to solve that determinants. So be very aware about it, right? Now, how to use these properties? So the first problem we will face will be that how to use these properties, or from where we should start, like how to think about which property I need to apply. We have 6 properties. How do I apply those 6 properties to solve this determinant and find out the value A? So for that, first of all, understand one simple rule. So let's say I have this. Understand this simple logic first of all. Now, let's say I have a 3 cross 3 determinant, right? And in that 3 cross 3 determinant, there are 2 zeros, either in first row or either in any row or in any column. Simple. Right? There are 2 zeros present in that determinant, and the 2 zeros belong to the same row or either to the same column. In that case, you can directly simplify that determinant by the rule of this. Now, this is not expanding. This is a rule of determinant only. And you will get it after expanding only. That is a different thing. I mean, you will get it. Why we can write this as this. I can simplify this determinant to this part. How? I will just simply expand it along the first column. And if I will expand it along the first column, you can easily see that this is simple. Okay, let's expand it along the first column. 1 into, this will be 7 into 5, which is 35, minus 24. Then if I go to the second element of this column, that would be 0. And the third element will also be 0, right? So this 35 minus 24 is nothing but the value of this determinant. 7 into 5, 35 minus 24. So if there are 2 zeros present in either one row or in one column, then we can simplify that determinant into a simpler version. So if we have a 4 cross 4 determinant and there are 3 zeros present in either one row or in one column, then we can simplify that determinant into a 3 cross 3 determinant, right? By deleting the row and column of that element. So let's say this was the non-negative was this was the non-zero element in the whole column. So I will delete this column and I will delete this row. I will take this element 1 and delete this row and delete this column. So whatever left will be the new determinant 5, 6, 4, 7. So can you please do this? If you understood this, you can ask me any doubts. And if not, then please find out the value for this. So we have this particular yes, sure. So Tharif, what we can do is we can simplify one determinant into its simpler version. So let's say I have some 4 cross 4 determinant. I can change it directly to 3 cross 3 determinant, right? If it satisfies one rule. Now the rule says there must be only one non-zero element in a row or in a column. If there is any row or any column present in that determinant in which only one element is non-zero. So for example, in the first case, I have this determinant. In this determinant, the first column is the column in which there is only one non-zero element. There are 2 zeros and one non-zero element. So I can reduce this determinant to a simpler form by a simple way. How? I will take that element which is non-zero, okay, and I will delete the column. I will delete this column, the column of that element, and I will delete the row of that element. I will take that element, write it as 1. I mean, whatever that element is, I will write it here into whatever is left after deleting the row and column. I will write that determinant. This is the value of this determinant only. With a string, there is one more rule, very simple rule. We will talk it about later on. But first of all, you understand this, that we can simplify this into this form, 1 into 5, 6, 4, 7. So for example, let's solve this one with me as well. So this is the second determinant. I'm trying to reduce this 3 cross 3 determinant into a 2 cross 2 determinant. I can do that, I know, if there is any one row or any one column in which there are only one element is non-zero. Or rather than you can say that if there are 3 elements in that row, तो 2 जीरो होने चाहिए, 1 नॉन जीरो होना चाहिए. अगर 4 क्रॉस 4 का होता तो वहां पे 3 जीरो और 1 नॉन जीरो एलिमेंट. There must be only one non-zero element in either row and in either column, right? Now, first of all, I will check my options. Second, if you check second column, एक ही element है which is non-zero, 9, right? Then if you check second row, then also there is only one element, 5, which is non-zero. So I can reduce in it either way. Either I can do it from this second column perspective, or I can go to second row perspective. Let's go to the second row perspective first. So according to second row, yes. So according to second row, there's only one element which is non-zero. So I will take that element, which is 5, right? And I will delete its row and I will delete its column. This is nothing but this. Did you understand it, Tharif, now?
Yes, sir.
Can you reduce it using the column transformation? I mean, the column way. We have second column as well here, in which there is only one element which is non-zero.
I think we can.
This one. This is your
Yes,
second
sir, we
column.
can.
Yeah. Take that element, delete its row and delete its column. Write whatever left. Yes, 3. So in second column, which is the element, I mean, what is non-zero element? First of all, tell me that. In second column, what is non-zero element? There are 2 zeros, right?
9.
9.
Yes,
So
sir.
take that element, write it here, 9. Now delete the row to which 9 belongs. That means you have to delete the third row, right? And delete the
Yes, sir.
column to which 9 belongs. Now, whatever is left, tell me that.
4, 7, 5, 4.
No, sorry. 4, 7, yes, that was correct. And
5, 0.
0, yeah. So that is the value of this determinant. That in this way, you can reduce any determinant. Now, there is also one more rule to this. The value can be negative or positive. If you are applying it on the first row, then the value is positive. If you are applying it on the second row, then the value you have to apply here -5. If you are applying it with 9, then also you have to apply it with -9. Right? Now you can check the value is same. It must be 9 into 5 into 7. Yes. And here also 9 into 5 into 7. Correct. The value is same in both the cases. It must be same in both the cases. So you can reduce any determinant with this rule. Now this is not expansion, first of all. This is reduction. In this way, you can reduce a higher order determinant to just significantly lower determinant, right? Or to its succeeding or rather preceding order determinant. So if the order is 3, you can reduce it to 2. If the order is 2, you can reduce it to 1. Until it is satisfying the condition that there is only one non-zero element. There is only one non-zero element to that in either one row or either one column, right? So in this way, we will try to reduce our determinants. We'll apply the properties of determinants on the given determinants. So let's say this example, we have this determinant. We will try to use our properties and we will try to reduce either one way, either one row or either one column into 2 zeros. So let's say I'm targeting this column 1. Why I'm targeting this? You will understand it as soon as you will solve 4 or 5 questions. You will certainly need some questions to solve. Then only you will get how would you apply these transformations clearly. But you have to understand one thing, that we have to make as many zeros as possible in a row or in a column. That should be our first goal. So whatever you apply, keep that in mind. Now, why I'm taking row 1, or sorry, column 1, because all the elements are in terms of A. So I can easily make 2 elements 0. How? Now let's check it. So I'm checking, what I'm doing is I'm applying a simple rule. See, there is no fixed way to solve this question, first of all. There may be a different way given in the example solution. I'm not even checking the solution. So there may be a different way, but there are more ways. The idea is simple. The idea is same for every solution, that you have to make as many zeros possible in a row or in a column. So what I'm going to do here is I will apply these 2 simple rules. First, I'm changing row 1, right? Row 1 changes to or rather, sorry, row 2. Row 2 changes to row 2 minus twice of row 1. Now what it does is, so row 1 is same, no changes in row 1. Row 3 is also same. Row 2 changes with this rule, R2 minus 2R1. So it becomes 2A minus twice of A, which is 0. Right? And similarly, 2 into 3A, which is 6A, or sorry, 2A plus 3B, I'm writing it here, minus 2 times of A plus B, which can be solved to B, right? And similarly, we will apply this rule here as well. So this will become 2A plus B. Yeah, 2A plus B. Shagus, do you need to ask something? Now, please feel free to ask. If you have any problem or any doubt, just raise your hand. I'll come back. Second row, second column. Oh, sorry, it should be A, right? It should be A, I guess. 3A plus 2B minus 2A plus 2B. So it should be A, correct. And it should be 2A plus B. Yes. Right. So the determinant, this first determinant, after this elementary row transformation becomes this. Now we have applied two rules here. First of all, we can change this to this, and the value doesn't change. Right. So we have applied first elementary transformation, and second, the property of determinant that the value remains same. No, Shavis, that is what the sixth rule says. Sixth rule is that you apply any column transformation or any row transformation on a determinant, its value doesn't change. And why the value doesn't change? Have we discussed it? Okay, 1 minute, 1 minute, 1 minute. So that's what we discussed actually in the sixth property. See here. If there's a determinant and we are applying any row transformation or any column transformation, then the value doesn't change. And the explanation is you can understand it from here only. See, can you write if let's say you have applied this transformation and the determinant changes to this, right? Now, using the fifth property, we can, okay, let's check this out. Yeah. So using the fifth property says that when can you add and when can you subtract two determinants? So rather, how can you even reduce a determinant into this form, right? I have shown by this arrow. So you can write a determinant into this addition or into this subtraction as well, right? Now we are applying this property 5 into property 6. Let's check this out. So I can definitely write this delta dash as the sum of two determinants. One is A1, A2, A3, B1, B2, B3, C1, C2, C3 plus K times C1, K times C2, K times C3, B1, B2, B3, C1, C2, C3. You can see that row 1 and row 3 are proportional. You can take K common, then row 1 and row 3 will be same. So this whole determinant is actually 0. So if you apply any row transformation or any column transformation, the value of the determinant doesn't change because of this simple explanation. You are applying K times of something. You can break this into 2. That K can be taken common. And after that, either two rows or either two columns will be same. So the determinant, the value of the determinant doesn't change if you apply your elementary row or column transformations. Is that clear? You can say that, right? Now, guys, please feel free to ask. Yeah, sure. Okay, so now the important point is to understand this transformation. The value doesn't change. That is the property. But the more important point is to understand why did I apply this? Because I knew as soon as I will apply this, this will turn out to 0. And similarly, I will try to make it 0 as well. Can you tell me the transformation which I can apply to make it 0? Any one of you? I will try to apply a transformation with the help of which I can make this 3a 0. Now this 3a can be made 0 with another a, with the help of another a. So I will need this, certainly this. The similar way I have done this, try to apply this rule again. Obviously not with the same values. So I have to change first of all R3, right? R3 changes to R3. Now I am trying to make it 0. So I can make 3a 0 with the help of 3a minus 3a. I have a, I will apply it with minus 3 and apply this. In the same way as I have converted row 2, I will convert my row 3 this time. And I knew, first of all, I already knew that the first column contains whole A. A को यार A की help से 0 बना सकता था. So I have changed 2A. उसको भी ऐसे 2A minus twice of row 1, right? Applied this rule. And then similarly, in the same fashion, I have applied this R3 minus 3 times of R1. तो अगर मेरे पास first column में पूरा A है, तो मैं row wise transformation करते जाऊंगा. Row wise transformation will give you results in columns. Understand this. And column wise transformations will give you results in rows. So see, I wanted to reduce the column. Because I knew the whole column contains A. A can be made 0 with the help of A. Right? So row wise transformations are helping out in reducing columns, while column wise transformations will help in reducing rows. This is an important point you have to remember. So first of all, now the process is simple. The algorithm is simple. How to apply, how to make, how to show that, or how to prove these determinants to equal to some expression. First of all, identify where are the same elements. Where are the same elements? Either they will be present in some rows or they will be present in columns. There must be a way, right? So try to first identify that. And the second part is, if you have found out the likewise items in columns, then apply row transformations to reduce or to make 2 zeros. And if you find likewise elements in rows, then apply column wise transformations to make 2 zeros in a row. Here I got the likewise elements in a column, so I applied row wise transformations. First row wise transformation, in which I changed row 2, and then I'm changing row 3 now. And after changing row 3, this will become A. Row 1 is same. There's no change in row 1. Row 2 is also same this time. There's no change in row 2. And the row 3 will become, so row 3 is changing to row 3, which is 3A minus 3 times of A, 0. The task has been completed. The task has been done. Right? I will reduce this directly now. To what? A times whatever this determinant is. No, sorry. No. My bad. Whatever this determinant will get. So first of all, find out the determinant only. Then this R3 minus 3R1. So 6A minus 3A would be 3A. And then 3B minus 3B would be 0. So this becomes only 3A. Then this will be 10A minus 3A will be 7. 6B minus 3B would be 3B. And 3C minus 3C would be 0. So this can be reduced. This can be reduced directly to this. Now there was one small confusion that when to apply positive sign and when to apply negative sign. So always change your columns. So let's say the same situation happened in column 2. So what you can do is you can interchange column 1 and column 2, make your column 2 to column 1, and then apply the rule. Right? So always change your columns. Always take first column and first row only. So अगर आपका किसी और में भी ये situation बन रहा है A00 वाला, change that column to with the first column and apply the simple rule. Now this can be written as A 2A plus B. This will be 3A and this will be 7A plus 3. Now if you solve this determinant, this is legalized to do. You can multiply A into 7A plus 3B minus 3A into 2A plus B. Whatever the answer is, you can simplify the answer. Okay, you can actually take 1A common. So this is A square, then this becomes 7A plus 3B minus 6A minus 3B. So B got cancelled out. This becomes 8. So the rule is pretty simple. You have to make 2 zeros in either a row or a column, and then reduce that 3 by 3 column, 3 by 3 determinant into a 2 cross 2 determinant. And with this example, I tried to actually show you two things. One, what should be the initial mindset with which we have to start. We have to start with the mindset that there must be 2 zeros in a row in a column. And the second thing is how these transformations are changing, how these transformations are changing the given determinant. So first thing, initial task. And second task is row transformations result in column reduction, while column transformations result in row reduction. Now we will try to use these logics, these two things with us, and we'll take these up with us and we'll try to solve some questions. The only way is to solve questions. There is no other way you can use, there is no algorithm to it. There are two simple rules, and for applying these rules, you will have to solve some questions. So the best part is, first of all, so questions on properties of determinant. So the best part is, let's say we get sometimes okay. So the initial heading is without expanding. Prove that. First is this. In some of the questions, you will be either given a column or a row which contains only one. For example, in this question, I'm giving you this one. Just a minute. Okay, so 1, 1, 1, A, B, C, and then A square, B square, C square. You have to prove this is a very important property as well. I mean, for JEE students, if you are preparing for some competitive exams, you should remember this. This is a property that if you have any determinant like this, 1A square, 1B square, 1C square. So basically, these are three geometric series, starting with 1 and having common ratios A, B, and C. The property says that if there are three GPs or geometric series, geometric progressions, are three rows of or three columns of a determinant, then the value of the determinant is A minus B, B minus C into C minus A, right? But rather than that, we have to focus on how to prove this. How can we prove this? Now, if we want to prove a determinant's value with some expression, the rule is simple, which we have defined. The first rule is our initial mindset. We know that we have to make two zeros in either one row or in either one column, right? So we have to find the likeable items. Now, the best part is if there is one column or one row in which there is only constants. See, we can easily multiply and divide constants and make zeros. So let's say I give you 4 and 1, and I ask you that make a 0 following some mathematical operation. So you can say that 4 minus 4 into 1, multiply this 1 by 4 and then subtract them, and you can make them 0. Very easy. This would be tough. This would be tough for a variable to do that. But for constants, we can easily do this, right? So in some of the cases, when you will be provided a determinant, there will be one row or one column in which there is only one present. These are the best cases. Easy questions. So what we can do is we can use this one to make them 0. So direct apply, row 2 changes to row 2 minus row 1. If I want to change my column. I have one column in which there is only 1, 1, 1. I want to make it 1, 0, 0. Right? So I will change this R2 to R2 minus R2. Right? And I'll also apply R3 as R3 minus R1. I cannot change R1 in this operation. Okay, you can apply as many transformations as you want. Okay, just always keep this fact in mind that whatever you are using to change another rows, don't change that row or that column. अगर आप एक ही step में in a simpler version, I say this, if you want to change a lot of rows or a lot of columns in a single step, you can perform as many operations as you want in a single step. The only constraint or the only rule is this, that whatever you are using to change these rows and these columns, don't change that row or that column in that particular step. So if I'm using R1 to change R2 or rather R3, I'm using R1 for both, for changing R2 and R3. So I will not change R1 in this particular step. I can change R1 in the next step, but not in this step, right? So after applying these two rules, what I will get is I'm not changing R1, so R1 is same. R2 will be R2 minus R1, so this becomes 0. This becomes B minus A, and this becomes B square minus A. Now this also becomes 0, R3 minus R1. This becomes C minus A. This becomes C square minus A square. And the value of the determinant is still same. This is the same determinant. I can reduce this determinant as I see that first column is the required column which I want, so I can reduce it. So this is called reduction, right? We don't need to write it. I'm just writing it for your convenience. So this is called reduction. Right? Reduction will be take the element, delete its row and delete its column, but only if the element belongs to first row and first column. So always make your first column or first row 100. You can make another row or another column as well, but just when you are trying to reduce that, change it to column 1 or row 1. Right? So this becomes 1 into delete the row and delete the column. You are left with b minus a, b square minus a square. Then this is c minus a, c square minus a square. Right? And you can take b minus a common from here. You can take c minus a common from here. So this becomes b minus a if you take b minus a from the first row, and this becomes c minus a if you take c minus a common from the second row. Now you are left with, it becomes 1 here because you have taken b minus a, and this b square minus a square can be written as b minus a into b plus a, from which you have already taken common b minus a. So you are left with b plus a. You are also taking common c minus a, so you are left with 1 here and c plus a in this place. Now you can easily solve this as well. So this becomes b minus a into c minus a, and this gets solved to c plus a minus b minus a. A gets cancelled out. So the answer is a minus b. Take minus common from here. Take minus common from here. Take minus common from here as well. This is c minus b. So this becomes b minus c. And this is c minus c. If you take two negative common, this becomes positive. And that is what was the RHS. So in first and the easiest type of questions, you will be given one row or one column जिसमें पूरा 1 1 1 लिखा हुआ. आप easily 1 की help से, एक 1 की help से, you can change another ones to 0. And you can reduce your determinant directly. This will be the easiest type of question. Now in the second type of questions, what will be given? These 1 1 1 will be changed to some other constants like 3 6 9, 3 2 4. There may be something, but constants only. Right? So not as straightforward as it seems. The only thing is this: you have to apply another rule. You will not be directly able to subtract them. Like you won't be able to R2 minus do this R2 minus R1. You will maybe applying R2 minus 2 R2 depending on the constants here, right? But still constants are given. Now the third type of problem, which was the toughest one, which we have solved the first example also, but that was easy because we find out likable elements very easily in that case, but it may be very difficult to get these likable elements. Now let's understand this with another question. So these questions can be tough to deal with, some of the particular questions. Now, let's take this one. So this is your example 15 as well. If X, Y, Z are different, and delta is equals to X square the question given is this, that X, Y, and Z are different, right? And the value of this determinant is given to you 0. You have to show that 1 plus X plus Y plus Z is equals to 0. So basically, first of all, understand, you will have to find the value of this determinant. How? Not by expansion. No, 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 no. You have to apply the properties of determinants only. And by using properties of determinant, first of all, reduce this determinant and put that expression equals to 0 because it is already given that the value of this determinant is 0. So reduce this determinant to expression, put that expression to equal to 0, use this information to prove this. Use this as well. Every information is useful here. Now, but the first part is to reduce this to an expression. Right? Now, this will be reduced using the properties of determinants only. Right? And this will be the important task, the most important task of this question. So let's try to reduce this delta. So delta is given x square 1 plus x cube, y square 1 plus y cube. Now, by seeing this delta, I'm trying to simplify this delta. Can you use any property? Like, what do you guys have in mind? Please share your thoughts or your opinions how we can solve this question. They may be wrong or they may be right, that doesn't matter. But we will just brainstorm over whether any rule is right or whether we can do this or whether we can do this. So that way, maybe I will be able to help you guys better. So you guys try to apply these rules. What can we apply here? This is a good question. Now try to simplify this. Can we use any property directly, first of all? Out of the 6 given properties, what would you like to apply here first? See, my first thought would be this, that the column contains 1 plus x cube, 1 plus y cube, 1 plus z cube. I can definitely break this. I can definitely break this to this. No? This is the simplest property which I can apply directly. I don't need to think twice. And I can also solve this. No? This is easy. In fact, you have already solved this expression. You just don't know it yet. I'll show it to you in a bit. After you guys first solve this question. Now, how to solve this one? This first part is easy. We have already discussed these kind of questions. Can anyone suggest how to solve first part? Second part थोड़ा tough होगा यहाँ पे, वो भी discuss करते हैं, but first part तो easy. You guys can easily solve first part. But how? Just tell me the steps. We have third column constant. No? Yes, Shavis. Please. Okay, third column is whole 1, 1, 1. So we can make 2 zeros, right? Yeah. So we'll apply row transformation to change it, to change or to reduce the column, right? Now apply this transformation and tell me the value. Try to solve this one, first part. I will also solve it, but in a much simpler way. But you can certainly solve the first one as जैसे ही मेरे को 111 दिखेगा, I'll be happy. I'll be really happy to see this because this can be directly reduced. तो 111 है, 1 की हेल्प से इसको 0 बनाऊंगा, इसको 0 बनाऊंगा, सीधा 1 0 0. अब इस थर्ड कॉलम को उठा के फर्स्ट कॉलम से रिप्लेस करूंगा, राइट? एक माइनस लगा दूंगा पहले. So I can solve it using that. Do I need to solve it? Please feel free to tell me. Okay, I can solve it in two ways. First way is what we have talked about earlier, that I can apply these two rules. So I will use this one. I'll use this one to change these two ones. So I will change row 2 to row 2 minus row 1, and I will change row 3 to row 3 minus row 1. And this will be x square 1, and then this will be y minus x, y square minus x square, and this will be 0. This will be z minus x, z square minus x square, and this will be 0. I can write this as negative times 1 0 0 so I can write this. Now I can directly, 1 will be here, so that doesn't change the fact. This will be written as y square minus x square, y minus x, z square minus x square, z minus x, directly this. I can take y minus x common from here because this can be written as y minus x into y plus x. So this will be minus times y minus x, and this will be, there will be a z minus x from second row, and this can be written as y plus x and 1, and this can be written as z plus x and 1. Now you can simplify this as well. This will be y minus z. So after simplifying, you will get this. First part will be this, right? Now the second part, and also this is the one way, first method. We have used this method in the previous question as well. 1a square, 1b square, 1c square. You have already solved this question. So you could have used the simple logic like this. So I am changing these two columns first. If I'm interchanging C2 and C3, this is the sign of interchanging, right? So I'm interchanging C2 and C3, so I'll have to put a negative. Then I'm again interchanging C1 and C2. So I'll put one more negative with a negative becomes positive. So this becomes 1 1 1. X y z, x square y square z square. So I could have followed another set of properties of interchanging, and then with the help of initial example, earlier example, okay, this one, we just solve the same question, guys. This first question, 1a square, 1b square, 1c square. So these determinants are very common. That is why I said in the before that these type of determinant is actually a property only. These type of determinants are very common. First and second both. This also and this also. They are common, very common. And they are same. Now you can see 1x square, 1y square, 1z square. You know the answer to that one from the previous question. This is x minus 1, y minus z, and z minus x. You could have used any way. to solve your particular first part. Now coming to the second. So the second part is x squared. Sorry. No. This is x. This is x squared. This is x cubed. Now this is y. This is y squared. This is y cubed. Then this is z. This is z squared. And this is z cubed. Guys, can you suggest me how to solve this one? What are the properties that we can use? First of all, focus on that. What can we do to simplify this? Can we take something common? Can we take some common from first two? X square and x cube. We can take x common, no? From the first row.
Yes, sir.
So if we take x common from the first row, what are we left with? 1 x square. Then going to the second row, I'm taking y common. I'm left with 1 y square. Then taking z common from the third row, I'm left with 1 z and z square. And this is the same determinant which I have just solved twice. So this will be x, y, z, x minus y minus z into z minus x. My delta was this whole determinant of first plus second. So delta becomes x minus y, y minus z, z minus x, plus x, y, z. Plus x, y, z, x minus y, y minus z, and z minus x. From which you can take x minus y minus z, z minus x common, then you are left with 1 plus x plus y, x, y, z. If you take this whole common from both the parts, you are left with 1 here, and you are left with x, y, z here. So this becomes, this whole delta can be written like this. So now you realize the first part of the question was the important part. Let's come back to the question. The question was, if x, y, and z are different, and your delta is equal to this, and your delta is also equal to 0, then you have to show that 1 plus x y z is equals to 0. Right? Now you have, first of all, the task was predefined. First task was reduce this to expression. We have done that. We have reduced this to expression, which is equal to x minus y, y minus z, z minus x into 1 plus x plus y, 1 plus x, y, z. Right? Then we have to use this. Now, what does it say? X, y, and z are different. If x, y, and z are different, what does that mean? Can you use this x, y, and z are different in the given condition? You already this expression, this whole expression has to be equal to 0. If this whole expression is 0, either x minus y is 0, or y minus z is 0, or z minus x is 0, or 1 plus x, y, z is equals to 0. Either this is 0, this is 0, this is 0, this is 0. Or there may be multiple zeros as well, but one must be 0. But we have to prove that this is the part which is 0, definitely 0. So how can we show that? Now, this says if x minus y is equals to 0 means x is equals to y, or y is equals to z, or z is equals to x, or there are 4 options. One must be true. in order for this delta to be 0. But it is already given that x, y, and z are different. So all these three conditions are not possible. If x, y, and z are different, it means they assume different values. Not possible. Hence, the only possibility is that this 1 plus x, y, z is equals to 0. So the point is, there will be some questions in which you have to identify how to use the properties, but just take these two simple things. First, the initial mindset should be that either in a row or in a column, I have to make two zeros. If I'm able to make two zeros, I'm able to solve the question. Just as soon as you are done with the two zeros, the answer is simple. You will definitely find out the answer. Don't worry about that. So first part is make two zeros. Now that is important. How to make those two zeros? If the constants are given, it would be easier. Let's say they have used 1, 1, 1. Very easy. If they have used some other constants, it will be tougher than the 1, 1, 1 wala condition, but it is still easy because we can use, we can easily use operations on constants. We are comfortable more with constants, right? But now when it's all the variables, right, then we will try to take some common. First of all, we will think about taking common. If taking common is not working, then we will try to find likewise items. If we are trying to find, if we are successful in finding out the likewise elements, then we will try to reduce them to 0 with suitable operation. Now we need to solve some questions over this. We will be solving 2, 3 questions, 1 to more questions on this in the next class as well. And after this, I think we are done with the chapter. So I'll check if we are left with something or not, but I doubt whether we are left with something or not. But before that, I will like to give you some questions. Try out these questions in the next class. Okay. I will also solve your queries, and as well as we will solve some more examples of this. So try to solve some questions. Now you can start here. Okay, we will use this property as well. But vanishes. Do you know what does vanish means? We try to solve these questions. Vanishes means this determinant is equal to 0. We have to basically prove this. Okay, so these are the questions 7, 8, 9. Then this is from 4.1.2, page number 36 or 36 here. 7, 8, 9, 10. In fact, 8, 9, 10, 11. I'm trying to find just some easy questions as well. Yeah, 13th. All the questions are important. So by the time we end these properties of determinants, you have to solve every question. But before that, I'm giving you some questions only. But you need to solve all of them. So as soon